Hey, what's up guys, and welcome back to the channel. In today's video, I'm going to be doing a quick little introduction to the different type declarations that you can make in C# and .NET. And so this just includes things like classes and structs and enums. So basically the different data types, or the different types of data types that you can declare in and use in C#. So the first thing we're going to be looking at today is the class. And this is probably familiar to a lot of you, especially if you've worked in any other object-oriented language or any other language with objects. The class is the fundamental type of data types you can declare. So this is going to be stored this is a reference type, meaning it's going to be stored, all of its objects are going to be stored on the heap, and the actual references to those heap objects will be stored within the context of where you declare the object. So for example, if I declare it in a function, there's the references or the memory addresses of the objects which will reside in the heap are going to reside in the function stack frame. And so that might sound a little confusing, but basically for reference types, there's the actual object in the heap, and then there's some memory address that you use to reference that object. And for example, if I declare it in a function, this memory address is in the stack frame, but the object will always be somewhere in arbitrary virtual memory. And so we're just going to look at the class. So the class is pretty simple. You can declare a method as with all, or as with most of these types. I'm going to just declare an object by just doing some class obj equals new, and I can just do object dot member behavior. If we cd here and then we .NET run, we can see that it will indeed call its member behavior. Okay, I did spell behavior wrong, but it's gonna say virtual behavior. Cool. Don't worry about this warning for now. I'll get to it. So it will say virtual behavior, which is what's in this method. And you might notice that there's something a little odd about this class declaration, and it's that it's implementing this interface. So that's actually the next thing we're going to look at, which is interfaces. And interfaces are also reference objects, or interface objects are also stored as references to some objects on the heap. And interfaces are like classes, except in that they only define some sort of behavior that an object can have. So for example, in a class, I can declare a field. I can declare a field. In here, you'll notice I'm not allowed to do that because these are only allowed to contain static methods and fields and behavior it's going to specify for some implementation down the line. So for example, these two methods specify some member behavior. So you can either provide a default implementation or force the implementer to implement some behavior. So here I've provided default. The implementer, so that's like this class here, you see there's this colon, it's implementing this interface. The implementer can choose to override this with their own behavior or not, but this one has no default behavior, this member behavior one. And if I control click to follow the references, you can see that in some class, this is our declaration for it. If I comment this out, you'll notice since no default implementation was provided, it's forcing us to implement this interface member. So that's why I needed to implement it here. And oh, something's lagging. Okay, and interfaces use what's known as virtual dispatch, or like a late binding call. So I have my some class object here, right? And now I want to get some reference to some class as an object of that interface. So now you'll notice that whereas in obj I could have accessed that field, I can no longer do that as when I have the interface, because the interface is only going to allow me to access the behavior associated with it. So right here, I have my two behavior methods right here. I'll first call the default implementation. This will revert to what we have here. And then I'll call the member behavior. And so we'll run this. And you first see it calls the default implementation and then our old virtual behavior method. Now, just to show you how virtual dispatch works, if I, for example, provided a default implementation here, I'll say another default. You'll notice this code never actually gets run, even though when I call member behavior, if I follow the reference, you're going to notice this is the declaration, and this is the default implementation. However, the actual implementation that we're using of our interface, the sum class, has provided a different method implementation for member behavior, and it's therefore it's going to use this and virtually dispatch the call to this method. So you can see that we use a sum class, and then we casted that implicitly to this isum interface, and we're going to use that to call our member behavior. So that's interfaces. They just specify behavior. Next, we're going to look at records. So records are, let me just delete all this. Records are also by default they're also reference like reference store data types, so they're stored in the heap. And I can also explicitly specify that by saying record class. It's just a style thing, but you can pass in some, or you can have some fields declared in your primary constructor right here, and these are going to be used for value equality. So normally when you try to use the equals equals operator on two reference objects, it's going to do something called a reference comparison, and that's actually going to compare their memory addresses. However, for a record, by default, the equals equals operator is overridden to actually compare their values, and these are the field values that it's going to use to actually perform that equality. So if I do some record 1 and let's say like hello 5, I copy paste that 2, and then let's make this hello 4. Okay, so and then we'll have 1 2 3. So you can see 1 and 2 are equal by reference, and I'm gonna just show you, or sorry, they're equal by value. I'll show you a couple different comparisons here. First thing we're gonna do is try to perform a reference equality on 1 and 2. We can clearly see they're equal by value, and then we're going to perform a value equality on 1 and 2, and then we're going to perform a value equality on 1 and 3. So while you can see that 1 and 2 are clearly equal in value, they both have hello and 5 as their fields, the first comparison actually comes out to false, and that's because these hold two different memory addresses, or these two references are referencing different locations in virtual memory, because I called the new operator twice, so they're actually not referencing the same object. It's created two different record objects. And you can see the second comparison is true, because this operator by default is overridden for these for records, and so it's actually equating hello and 5 and saying that the two objects are true or equal in value. And then you can see obviously 1 and 3 are not equal in value, as the 4 and the 5 are differing values, so that intuitively returns false. So that's records. It's just basically helps you, or it's a ease of use feature for value equality. Nowadays in my projects, I don't really find myself using records. Instead, I override the equals equals operator and then implement this interface called iEquatable, which forces you to implement the equals method just to perform equality checks or value equality checks. And then one final note on record is that I said before you can write record class. Well, if you didn't want this to be stored you didn't want this to be stored by reference, if you wanted the entire sum record to be stored by value and compared by value, and I'll talk about what that means in a second, you can just write record struct, and now it's going to be stored by value. But I'll keep it as a class for now. So talking about value, we're now going to move to structs. And structs, as I just mentioned, are stored by value. And what that means is the contents of the struct are stored in wherever their context is. So before we saw that for reference objects, what's actually stored in the context is the memory address or the reference to the heap object. So if I gave the example before, if I declare and initialize a reference object inside of a function frame, what's actually going to be stored in that function frame is the memory address, which will then indirectly reference that object on the heap. Here, if I declare some struct variable in a function, it's actually going to store the entire contents of that struct that struct object in the function frame, so in whatever the context is. Likewise, if I have a struct as a field within a struct, it's going to store that entire struct's contents within the entire enclosing struct, or within the entire enclosing type. So by that logic, if I declare a field in SumStruct of the same exact type, SumStruct, this is actually going to be illegal. And the reason is, as we talked about earlier, if I store a SumStruct here, it's going to store the entire allocation or the size of SumStruct inside of SumStruct. And you can see this is going to cause an infinite loop, because in order for it to calculate the size of SumStruct, it first needs to calculate the size of SumStruct to store it within itself. And you can see this is impossible, because it's going to keep recursing over itself until it finally realizes that, or it finally hits a limit, and it's like, wait, it's using itself in the definition of itself, which doesn't really make sense. So that's just how structs are stored. Other than that, you can use them pretty similar to reference types. Right here, I have implementing the same interface, and this is actually going to perform what's known as a boxing conversion. So if I declare SumStruct object equals new. So right now you can't see it right now, but the compiler has implicitly declared a function around this code. So this is within the main method. And so now I've declared this object in my function stack frame. So if I now wanted to actually use the interface behavior on this, what I would have to do is perform what's known as a boxing conversion. So I'm going to declare an ISUM interface as interface equals object. And you notice this implicitly converts. Now what's actually happening behind the scenes is it's taking the value. So as I said before, structs are stored by values. Taking the value off of the stack, the function stack, and it's still on the stack, but it's gonna copy that value into some heap location in memory so that it can mimic storing this struct as a reference type, and then it's gonna assign that to as interface. And so that's gonna allow me to call my virtual behavior. I can call my member behavior right here. Instruct. Cool. So that's basically structs, and they're stored where in the context of, or they're stored wherever their context is. So that's that. And then there's ref structs. Now before structs were only stored where their residing context is. Now we have ref structs, and these are only ever stored on the stack ever. And the reason for this is they can hold different ref fields, which allow them to hold pointers to, manage pointers to different variables in the stack. And the framework or the runtime needs to keep these protected and make sure these references never get leaked in order to avoid memory corruption bugs and other things like that. So that's why these can only ever stay on the stack. They can never leave the stack. That means you can't put them in an array, because that array would be stored on the heap. You can never box these. So in newer versions of C#, they can be implemented. You can implement interfaces, but you can never actually convert to that interface because that would require a boxing conversion. So you can never box these, and yeah, you cannot put these on the heap. And only a ref struct may hold another ref struct. Sorry, I think something cut out there. You can never have a struct or class which has a ref struct as a field. Only ref structs may hold other ref structs as fields, and that's because if that enclosing type makes its way onto the heap, then now you've leaked a ref struct reference onto the heap. So other than the fact that these things may never leave the stack, they behave the exact same as structs. You just can't do a lot of stuff like use interface behavior and other things. But I'll show you that I can create my object of, what I name this, sum ref struct equals new. I'm gonna just make this one public. And you'll notice I have an empty constructor in here. The reason for that is, if I comment this out, the compiler actually requires you to explicitly declare a constructor if you're going to have some field initializers for any type of struct, whether that be a ref struct or not. I'm not exactly sure why they want you to do this, but I think the reason is that normally when you declare a struct, if I never put this new operator here, what it would do is it would reserve the memory for it. So if I didn't have, if I didn't have this initializer, well, now val is unassigned, but it would reserve from memory some memory for this, so I could just do, it would all be zeroed out, so I could set the value, then I could print it. But now I think the reason they want you to declare constructors just to make it explicit that if you try to make this declaration, you are no longer initializing any of these fields, because it's that declaration is just reserving memory. And if you actually want to initialize all the fields, you're going to have to call a sum function, and that's going to be a constructor. So the last type before I close out the video is an enum. So an enum is just a nice way to have constant values assigned to names for groupings of similar items. So let's say I just want like the user to pass me, or the end user of my API to pass me a type of fruit to some function. And I don't want to parse that as a string, because that's over the top for such a simple option. And plus I'd have to just parse or I'd have to have checks for string equality. Here I can just use an enum. If I have some hard-coded values, I can just give them names: apple, banana, strawberry. It'll default to starting from 0. And if I now declare a fruit, I can say oh, this is a banana. And if I write this fruit, it's going to say banana. The cool thing is that you can use these just like normal integers. I showed you before that these actually have integer values, so banana is 1. So if I convert, instead of saying fruit.banana, if I just did fruit and I did 1, it's also going to say banana, because that's the value. 2 is going to say strawberry, or whatever I put there. Strawberry, yeah. And then something even cooler is banana and banana are both 1. Fruit 1, fruit 2. Fruit 1 plus fruit 2. Oh man, I'm going to have to convert one of these to an integer. If you actually convert these to an integer, they'll give you the underlying value. So if I add 1 and 1, that's banana plus banana, it's going to give me strawberry, which is 2. So you can use these just like integers. They're pretty useful for things like bit flags, but yeah, they're just used to assign names to constant values with some grouping. So that's it for today's video on the different types of types, I suppose. If you enjoyed today's video, make sure to leave a like and subscribe. Helps out a ton. And I'll see you in the next one.